Hello, people. Nice to see you again. My name is Mihai. Some of you already know me, and I am the host for this event. During the presentation, please keep your microphone muted and use the chatbot for questions or anything that you would like to ask the presenters. I will make sure we answer all your questions at the end of each talk, and we can actually play a little bit with time and accommodate each and every question. So don't worry about it, just put it in the chat pod. I want to remind you that all our events are recorded, and soon after we end, the recording will be published on YouTube along with the presentation slides. During the second presentation, I will share a feedback form with you. Please take 2 minutes to fill it up. It will help us improve the overall event preparation, and it will also give us quite a good idea about what you would like to see next. That being said, I will welcome Gary, our first speaker today.
Hello, thank you, Mihai. Just before I start, is my microphone coming through clearly? Because I do have some problems with my microphone.
Sounds pretty
loud
good.
Enough, working, cool. And a special hello to Bert, who I worked with in South Africa, and he joined in. Hey,
Okay,
Bert.
so we have people from South Africa. That's amazing.
Yes. Okay, so let me. Okay. So I really struggled to come up with a title for this talk. There was something in particular that I wanted to talk about, which is somewhere in this talk, and I labeled it scaling a Perl worker, so it's kind of relevant. I'm Gary. I'm an SRE at Booking. I work, and where this talk comes from, I work on maintaining the reliability of some of our big services. So Booking.com and SecureBooking.com are their Perl services. They've been they are the legacy kind of code at Booking and the legacy services. That's what I do, and that's where this talk comes from. But I wanted to mention that this is also relevant to Python. Perl is not special in this regard, and this talk isn't outdated. This applies to Python. In general, it actually applies to uWSGI. And I think anything that is single-threaded can probably get something out of this. Anyone running single-threaded languages. So yeah, that's why labeling this talk is kind of difficult. But I thought I'd label it scaling a Perl web worker, because then we'd maybe have some controversy. Maybe fewer people would come watch. Anyway. So what we're talking about here is, in terms of setting the scene for what we're trying to scale, it's code that's been given to us to run on servers. So we're not going to talk about how we'd optimize the Perl code or anything like that. This is more about having a piece of code that we want to run and scale up on servers that have a fixed amount of RAM and CPU. Generally, I'm going to kind of be referencing a server that's somewhere around the 64 gigabytes of RAM and let's say like 32 threads, something like that, or 16 threads. It's not super important, but that's kind of the size server that we work with. Actually, the servers that we use are about double that, but we deal with servers that have NUMA, so they have two sockets on the boxes, but that just complicates things a bit. So I'm just going to, anyone that's familiar with this, NUMA just doubles some of the numbers, but yeah, that's what we're working with. So how does this all work? We have a process. We're running this on Linux. We have a process that we want to serve web requests with. So in terms of our stack, we run on bare metal boxes. We run with an Nginx in front, and then uWSGI, which runs Perl. So if we just talk about one Perl worker, what we're loading in there is, first we're going to load Perl. Then we're going to load some stuff on top of there. So this is all taking up more and more memory. So we load the booking core libraries, which are quite big. Whoops, the wrong direction. We throw in some templates in there. That takes up quite a bit more memory. Throw in some translations. Then once we get to actually serving the request, there's the context on the request, the variables that we're setting and saving in memory, their caches, and this all grows and grows to the point that we can have, in the case of booking, well, let's not get to numbers yet, but let's get to numbers. In the case of booking, this whole thing can get to somewhere around like the 11, 12 gigabyte mark. We're dealing with fairly beefy servers, so this would scale down or up depending on the size of your servers, but this single-threaded worker is quite big, and this can serve one request at a time. So if we're looking at say a box of 32 threads, this is going to not fit in RAM, and generally we would run more workers than threads that we have on the box. So we can straight away see that we're going to hit a bottleneck here in terms of the memory. If we just had to run, say, I don't know what this would work out to on a 64 gig box, but something like 6 workers, a little bit, 5 workers, and then we run out of memory. And that's not even taking into account the operating system and various other overheads. So what do? Well, what we do is we split our worker into 2 pieces. So we load a whole bunch of stuff into a parent process, and that's this line that I've. Can you see my mouse, by the way?
Not
Or
really.
is this pointing not working?
Oh, actually, it works. Started
Okay.
to show.
Okay, cool. So you can see my mouse. I like in these talks on BlueJeans, I tend to like point at the screen, which obviously doesn't really work. But if you can see my mouse, that's great. So all of this stuff below here is kind of the shared stuff that all of these workers are going to be using exactly the same thing. So these 10 GBs, we rely on a feature. Well, we kind of hand this off to the kernel to deal with this memory in a really clever way. It's a feature called copy on write. I don't want to go into depth on this. It's worth reading on. But basically, these child processes that we're going to spawn will look at the same. We'll get a page from the kernel that reads through onto the memory of the parent process. It will only, and this is where the word copy on write comes from. It will copy that onto a new. It'll have to allocate physical memory only when that memory gets written to, because that's when it'll change. So we rely quite heavily on the semantics of copy on write in order to have, well, if we do the math now, it actually gives us quite a lot of spare memory, because we now have 10 GB once, and then for each child worker that we want to spawn after this point, it's just going to be the caches and the request context and whatever other stuff people want to throw in there that's per request. So there are 2 sides to this now. We have the parents. So you'll see through my slides, I got a little bit not uncomfortable. It's a little bit of a joke, but I tried to use the PC naming, so I kind of crossed out master. And there was one point where I was writing it down about child workers. But anyway, so the parent process will load in all of this stuff. This strictly needs to be stuff that does not change on the workers. If anything goes into the pre-fork that is going to change on the workers, then those pages are going to get copy on write, and it's going to take up a whole lot of extra space, and that will cause problems for us. And similarly, the other side of this is that the child process should not contain data that is going to be repeated across the workers. So it's a little bit tricky to work out whether something should be on either side, and there are different ideas here, but you can roughly see what should go where. And this basically allows us to use all the CPU. We can utilize the CPU as far as we want. We tend to run about 1.4, 1.5 workers per thread. So the reason that you can run more is because very often Perl is not doing work. So when we make a call out to a dependency, MySQL or something, then there's going to be some time where that can go off CPU and something else can be scheduled. So we can actually run more workers. I think it's somewhere around 1.4, 1.5 that we run. So I don't want to just, I find it really difficult to just talk for 30 minutes and then get to the end and then reference back any questions. Are there any questions at this point about what we've discussed?
So looking at the chat pod, there is no question so far.
Okay. I can't actually see the chat, Mihai, so if you can just stop me when someone asks something, I'm totally okay with that.
Okay.
Okay, so we'll continue. So now we have, I need to try and figure out what, so let's look at this from a slightly different angle. And we'll actually come to an incident that, and sort of an outage that happened to us about 6 months ago or so. If we look at a box with 64 gigs of RAM, so these are all hand-drawn notes, so sorry, I couldn't update some of the numbers, but this is a 64 gigabyte box. We load in the parent process, and let's say that takes about 10 gigabytes of RAM. There we go. So I've minused out like, say 14 gigabytes for the operating system. That's too much, but let's just say we're dealing with 50 gigabytes that we can work with here. So we have 10 gigs for the parent process. Then the children, if we have about 40 of those children, we can split up that. I said it was something like a 1 gigabyte size on those on the workers. So this uses all our memory. So we have all 50 gigabytes used, and now we want to do a rollout. So I'm just mentioning here that each of these are using the copy on write and the shared memory there. Now, when we want to do a rollout, this is going to spawn a new process that is not going to be using this old parent libraries and code. We want to load in the new code, but there's no space. This is something that actually happened to us, that we ran out of memory. And what happens in this scenario is the killer is going to come around and just kill things by whatever heuristic it uses. So any of these processes could hopefully be killed in order to make space for the new parents. But in some cases, our parent process was being killed because this is quite a fat process. So the kernel would come around and kill this process, and we'd get stuck. So we got to a point where we actually can't roll out. And this is quite a big problem. And when we hit this, there were a few ideas on how we can fix this. You might be thinking of some of those. For example, just reduce the number of workers. That's a fairly quick fix to this. This will give us space in terms of memory, but we would have to increase the number of boxes in that case in order to keep up with the capacity. Another option, I should have actually made this the last slide, but clean up the code. So right at the beginning, I mentioned that this is just code that's been given to us to run on a production box, and one very reasonable way probably of fixing this is to go in there and find out where the memory leaks are, to maybe make that, why is that master process 10 gigabytes? Some of these questions are very reasonable, and this is another way of tackling this problem. But I'm not going to go into that, because the reality on cleaning up the code is it takes time. It's not on the order of days or weeks probably to fix that. Maybe they're quick wins, but it turned out they weren't. Another option is to make rollout slower. So
I think
hello?
we lost you.
Yes, sorry, I
Maybe-
stopped. My network does drop from time to time. I did stop. So I'm going to come back here. I think where you lost me was making rollouts slower is an option. Something that I forgot to mention is the way we do rollouts. If I just jump back to the slide here, is we do rolling upgrades so that we never actually take boxes out of the load balancer. We keep serving requests to this box the whole time we do a deploy. So what happens is this new parent gets spawned, new workers start getting spawned, and they all uWSGI uses one socket for these, and it passes that socket to both parents, and we're serving traffic the whole time. So one option here is to make rollout slower. So we can just take the box out of the load balancer, kill the old worker, bring up the new worker, problem solved. But our rollouts are not super fast. I mean, this doesn't happen on the order of minutes, but we didn't really want to slow down rollouts here. That was not really an option, but it's reasonable to do that, I think. So what do we do? I'm going to jump now to the way uWSGI cycles through workers. So these workers don't live forever. They get spawned, and they will have a certain lifetime, which is configurable on uWSGI. It has three basic ways of recycling these. You can either specify an amount of time you want it to live for, an amount of memory you want the worker to consume before it gets killed, or an amount of requests that you want it to serve. All of these don't quite fit with our problem, because those under a deploy, you want the conditions to change, and we have a mechanism where inside Perl we keep track of. Perl actually recycles the workers for us in a fairly sophisticated way, and I'm going to go through how we do it, and then hopefully you can see why we think it's better than using uWSGI to do this. So that's just setting the scene for where this comes in. It's basically an alternative approach to cycling through the workers. So I have drawn here a graph. This is memory utilization on the bottom, and on the left-hand side here is the expected number of requests that we want a worker to serve. So either expected number of requests or time. It's fairly interchangeable, but I'm going to talk about the number of requests that it served. And there are two extremes that we have. Under low memory utilization, so let's say the box is close to 0%, we want these workers to live for really, really long. So those workers can get fat, they can leak memory, they can build up caches, they can do what they want. There's spare memory available for those to do that. So we want to use this memory because presumably those caches are being set up to make things faster and better for the customers. So yeah, we're going to live for some max age. Whatever, an hour, 2 hours, doesn't really matter. On the right-hand side, when we're under extreme memory pressure, say close to 100%, we want to limit the recycling of these workers to some maximum, and this is kind of some sort of arbitrary number. We try and fork at a rate of 1 per second. So we don't want to spin up a new worker much faster than 1 a second, and that's this is where we want to move between. Depending on how much memory is being used. And it's not immediately obvious how you should draw the line between these two. initially, when this was rolled out, we actually just drew a straight line between them. We did a linear regression, and depending on where you were, that was how many requests we would expect you to serve based on that line. That has some problems, because when you get to a high memory rate, it doesn't push you back down in memory fast enough because of the way the linear thing works. So we had a look at this, and we drew a line like that. So this was, I was working with this with Eve, and he went to go look at sigma functions, activation functions from machine learning. Is where they're commonly used. And this is the inverse of a logistic function. And it has some really nice properties. So just to explain this graph a little bit, I think I did it with words here. On the left, we try and live for a really long time until we get close to the target memory utilization that we want to hit, let's say 80%. Anytime we're using less than 80% of the box's memory, we will really serve a lot of requests and let the worker live for long, quite far. And on the right-hand side, the workers will cycle themselves quite quickly, approaching the maximum fork rate, and it will start to converge on this target memory utilization. And the fact that we have this one parameter of target memory utilization is really, really useful when we come back to discussing how this can fix deploys. Just to quickly visit the logistic function, because I find this super, super cool. That's what it looks like. It has two parameters. It has this k and this x0, and I've got a little demo here that hopefully will work. Okay, it works. So just to see what these parameters can change. Come on. There we go. So we can set the position, which is the x0. So we can set the target utilization. So if we want to change this to 50, then that graph will jump to the left. So we can set this wherever we like. And we can set the steepness. So we can make this kind of flat, and make it approach things slower, or we can make it really, really steep. So almost like a step graph. So that's the logistic function. It has these, and you can scale this graph with a min and a max and invert it and whatever. But it's essentially that function, and it's super simple to calculate. It's just an exponential, and that's how it works. And I don't want to go too much into that because I actually think I might run out of time. But logistic functions are used a lot in machine learning, and they also used in a lot of mathematical modeling of populations, for example. Okay, so now we have an expected number of requests that we want to be able to serve. Now, how do we kill workers once they reach that number of requests? The logistic function pops up again, actually. So we have this amount of time or number of requests that we want a worker to serve, and we draw in the logistic function. This is now the inverse of it with different parameters, and we use it in a slightly different way. What this will do is this is a probability of killing the worker, and when the worker starts out its life, it has a chance of dying, a very small chance of dying, and there's a reason for that. The reason, or the steepness here, is how we don't want all the workers to die at the same time. So when we do a rollout, we don't want every worker to die after 100 requests, because 100 requests will come by and we start cycling through and we have these spikes in CPU. So we really want some kind of smooth behavior here. So we give them a random chance of dying early on, but this really gets high when it gets to this expected lifetime. And when it goes beyond the expected lifetime, the chance approaches 1 fairly quickly that this worker will die. And that'll average out on this number. Same function, really cool. You should check it out. Now, so I had to take this slide on a different camera that's really terrible. But anyway, how does this help us? And let me make this big again. How does this help us? Well, now we have this one number of target memory utilization that is the one parameter that we can send into our worker lifecycle algorithm. And it's really useful because when we are in a deploy, we tell that all those workers to change their behavior. We tell them, hey, by the way, you don't want to hit this amount of memory now. You want to hit half of that. You want to make space for the new worker for the new master process to be spawned and for all the new code to be rolled out. So that's what we do. We halve it, actually, is exactly what we do. And it changes the slope to look like this. And so all of a sudden, workers are going to be sitting. So we converged on this point here. So all of a sudden, workers drop down to there, and they start serving way fewer requests, and they start getting cycled much quicker. Yes. So that's basically what solved our problem. So when we tell all these workers that are sitting here to start cycling through themselves faster, one of the cool things about the way this works is we will kill workers when they get old. And when a worker is old, it is going to have got fat. The only way a worker can get fat is by serving requests and leaking memory. And so the more requests a worker has served, the sooner we should kill it. So we start killing off all the big workers here, and I just cross these out. We make space for the new parent to be created, and these are all being killed off at a much faster rate. I should have drawn these lines a bit further, but these are all getting killed up at a much faster rate, and these new workers are not getting killed off at a faster rate. These are living for longer, and they are much smaller. So those lines are a bit smaller together because the caches haven't been set up yet. And eventually we get to the point where all of these workers should be dead. I should have drawn those lines further. All of these workers are dead. This is the new master process. All of these workers should be spawned, and eventually we can just kill everything below here. So we can now roll out. And not only did this fix our rollout problem, we actually use more memory, and it's really a good thing. So the reason we want to make space for these workers to live for longer is so that the developers can set up in worker caches and trade memory for latency in certain places. And if we have the memory sitting on the box, we might as well use it. So we're now able to target how much memory we want to use. And that's it. That's any questions?
Thank you, Gary. Let's see, what do we have in the chat pod? Any questions from the audience? Anything for Gary to answer? No, looks like everyone understood everything. And if there
Sorry
are
if I went too fast. I'm happy to jump back to any of these points that I went too quickly through. I just wanted to make sure that I managed to get through the whole talk.
Question.
Yes.
First of all, thanks. That was interesting. So before this fix, were we actually requiring double the memory just for the rollout?
Not double. So if we come back here, we required, the way the rollout works is we need to have this new parent in place. And so we required 10 gigabytes of memory to be available. That's all we needed. So the problem only occurred when we ran out of that spare 10 GB, and then the killer would start coming through. We didn't need to spawn up all the workers straight away. So once this is live and starts spawning its new workers, these old ones will start dying off quite quickly. So we don't need double the memory, but we do need the amount for the new parent to be spawned.
I would argue that we were kind of just lucky because we had the old formula just configured to like basically use all resources except for a little bit left over for the system. And it just happened to be that our startup process fit underneath that system limit. And there was really no provision at all for scaling that over time. It was like hard coded in the code, and it was just at some level dumb luck that we went for as long as we did without having this problem.
Mm-hmm. Thanks.
Any other questions, guys? Questions for Gary or Eve? Hey, Eve, nice to have you here.
Hey guys, I'm really sorry I missed the beginning of this. I thought this was a really cool presentation from Gary. He showed it to me earlier. Even for me working on this, it's actually pretty cool to see because this distilled many, many long conversations Gary and I had into like a pretty succinct view of it. I really like what you did here, Gary.
Cool, thanks.
Thank you. Okay.
Is there anything that you want to cover, Eve, that I hacked?
No, I mean, I think one thing is just like,
highlight?
I think one thing is just that like there's a certain level of experimental play here. You kind of need to understand how a lot of different moving parts are working with each other. The revised version of the algorithm that you and I came up with, I think, is more responsive, but there are a number of knobs that can be tweaked for other scenarios where you might want to have slightly different prioritization or where there's other weights involved or things like that. But I think the fundamental idea is pretty cool. One of the hard parts I think we had was what you're trying to avoid is like a thundering herd off the cliff, right? So you don't want like if you want to have like a sort of cap on the lifetime of your workers, you don't want them all to run off the cliff at the same time because then you don't have any workers available at all, right? But then that then introduces the notion that you have some kind of coordination principle between your workers to ensure that you don't run them all off the cliff at the same time. And so the really nice thing about like this idea in general, even the first one is to basically use probabilistic modeling to represent that underlying coordination feature. So like looked at just as at the behavior of a single child, it doesn't really make sense. But you get this emergent behavior that's basically the same as though you had a hidden hand pulling the strings to like keep things in the right zone. And I think like personally I really like I think that first of all, the best solutions to distributed problems have that kind of self-solving effect. But second of all, I think there's like, sometimes it's unavoidable that you have to have a controller process, but it's really nice when you can get it as an emergent process from a bunch of actors following the same rules, but not really aware of each other or doing anything depending their state on any other worker's state. I think it's a really powerful model of understanding, distributed computing that should be used as much as possible when it is possible. Like not overused, but personally.
Yeah. So one of the one property that on here is this K. And what K does is it spreads this, I can't draw on here, but it affects the steepness of this basically. So the steeper you make this, the closer you get to that thundering herd problem. And the more spread out you make it, the longer it takes to converge onto like random distribution. So, and the more chance you have of workers living way too short or way too long. So that's one of the parameters that Eve's mentioning that we really need to play with here.
And one of the symptoms of, like, I would argue that one of the symptoms of a too steep an angle would be that you start seeing like harmonic effects in your worker lifetimes after like a deploy or state change, because you know, when it's when it's at the right angle, you basically don't see any at all.
So it's damping, and actually what you want to find is you basically want a critical damping, so that it gets to converge as quickly as possible. If you go too low, it will never converge. If you go too high, you have those oscillations, like you say. So that was kind of what we experimentally try to find.
Yeah.
Okay, I think we have a question in the chat. So
Sorry, I can't see the chat.
asking,
If you could repeat it.
I can actually read it for you. Abhilash is asking if are the requests dropped because of killing workers, or do we have a graceful way?
No, so actually this is completely graceful. So what happens is the worker will only be able to die after it's served the request, and then uWSGI will poke Perl and say, hey, you're done, and then it just won't serve another request. And the process, so if I just go down here, the old process will not, this parent process will not spawn new workers, whereas the new one will spawn new workers. So you slowly get this like draining and rising on the new stuff. And on the box, Nginx actually has no idea that this is happening. Like Nginx has no concept of a deploy.
Yeah, I think one thing that's worth mentioning here is that one of the reasons that we do this kind of stuff inside the application is that we want to be able to send out a bunch of status telemetry data as part of the shutdown process. So we want like our code to own the child shutdown process. So like there's a bunch of specialized data that's only sent on the last event being sent by a worker. And so when this memory management, when this logic kicks in, basically sets a flag that causes us to like trigger our last event and then gracefully shut down that worker, and then effectively uWSGI at one level or another spawns a new worker to replace it. So like we're sort of sitting these workers are sitting one queue down. So in general, the process one level above will have a pool of workers. So we are arranging to shut one of them down. One of the things we want to do is manage the number of new workers that uWSGI spawns in any given second as well. So we're trying to aim for spawning at most one new worker every second, because there's a certain overhead to spawning that new worker, and if you're spawning them like too rapidly, you can kind of overload the box a bit.
Thank you, Yves. Thank you, Gary. It seems like we don't have any more questions, so I suggest we go to the next talk. Yoann will tell us about alerting.
Hi, guys.
Hey, Yoann.
Hi, everyone. Do we have like a short break or something, Mihai, or should we go directly for it?
I think we can go directly.
Let's go. Need to share my screen. Can you see my screen?
Yes.
Okay. I don't know what you're seeing. I hope it's the presentation. Okay, so hi everyone. My name is Yoann, and I'm working as a nursery at Booking.com. So I'm actually working nearby to Gary's team, so it's pretty fun. And today I'm going to speak about something that you don't want to hear after work, which is alerting. So I'm not an expert in that. I call it art, not because we master it. I call it art because I think that it's always kind of a compromise. There is no perfect alerting system. There is always compromise between the quality of a service in the end and how often we want to manually do something. Okay. You're seeing the agenda, right? I have no idea what you're saying.
Yes, we see it.
Okay, perfect. So we'll go through the basic of alerting, like what we used to do on technical metrics, and then we go through like the SLO part, the error budget, and practice, and seeing how you can make it generic, which is very interesting. So alerting on technical metrics first. So we all have systems that have like lots of dashboards. I put some screenshots of like Grafana dashboards. You can have Prometheus dashboards. You can have Elasticsearch dashboard. You can have whatever you want. In the end, most of them are showing either business metrics, either technical metrics, either some like hardware system things. They all show something. But if you look at this dashboard, you have actually no idea of what is the status of your system. But yeah, it's good already. So if we go back like 2 years ago, this was our monitoring system, and we were using alerts based on that. So you take all of these things. You can take a few examples here, like you take JVM, you take CPU, you take the error rate on the box, something like this, and you'll put metric and an alert on all of them. That detects a lot of things, but there are a few problems with that. First is that there are way too many alerts. So for the system that we support, we have thousands of servers. If you start putting alerts on all of those boxes, you will get alerts all the time. So you will have to like do alerts on aggregated stuff. But anyway, at some point there will be a few number of boxes being able to trigger an alert. The second problem is that the business impact is unclear, or often actually completely unknown and inexisting. You will wake up, you will work on something, try to fix it, and at the end you will see that no one knows the problem because actually there is no impact. So this is like kind of a bad limit of this kind of alerting. And the last thing is that it is hard to prioritize the response. So you'll say you're in the middle of the day, you're working on something, and you get a new alert, a new page. But as you don't know the business impact of it, it's hard for you to say, okay, I'll drop everything and I'll work on that right now. Or maybe it can wait. You actually don't know. And that's all of the problem. And basically at the end, it just becomes noise. So you get alerts after alerts after alerts. And you just start ignoring them. So you have a very good number of alerts that gets ignored all the time. And the people that actually have to react to them, they also get tired, not only physically, like this guy in the picture, but also mentally. Like they get exhausted of just doing operation and just reacting to alerts. And the problem is that actually we don't have a clear vision of what an incident is in this context. We don't know what is the impact or anything. So when we see a high CPU on a certain number of boxes, is there an incident or not? Well, it's possible, but we don't know it. If we see high P99 latency of many boxes, is there an issue? Again, maybe, maybe not. If your customers are impacted, yes, there is a problem. But how do we know that? Well, it's actually simple. We have a tool for that. We use the SLO. So the SLO are a representation of your system that is agreed upon by your customers. So if you start impacting your SLOs, then yes, there is something wrong. If your SLOs are fully fine, there is nothing at least visible. So no reason for you to alert on something that is supposed to have no impact. The supposed to is very important because you always aggregate stuff, and it's possible that some people see an issue that you cannot see at the end, but it's usually a good proxy. So okay, let's stop now putting our alerts on the technical metrics, and let's put them on the SLO. So let's do that. Quick reminder, just in case. What are SLIs? What are SLOs? So an SLI, basically, it's kind of just a metric. It's a measure of your system that represents something. For example, the availability, like the percentage of requests that get 200, or the percentage of time where your system is actually responding. It could be also the percentage of requests that are responding within a certain amount of time, for example, like a latency. It could be about data quality. It could be about many things, but it's just a metric. In itself, it doesn't mean much. When you consider the SLO, basically you start to put an objective on the first metric that we discussed. So basically, if we spoke about the availability, so basically you answer with 200s, on the end, you will have say that, okay, if my availability is above 99.99 for a week, then I meet my objectives. So then you start to have a threshold of 99.99, and you can start thinking, okay, maybe I can actually alert on that, because if it drops, potentially the customers are actually impacted. And this is what we did at the beginning. So we have the SLI, we have the objectives, and we just draw a line and alert. The problem with that is that it doesn't really fix knowing if there is an incident or not. I just zoom in the same graph here. If I look at the first drop in the SLI, like there's a very steep drop. It's hard to know if it's an incident or not. Like it didn't last long, was strong. Is it? Is it not? I actually cannot tell you right now. If we look at the second potential incident, like we just go below and above the line for quite some time. Maybe it's actually bad on the customers. Maybe it is not. I again cannot tell you. The thing is, we are focusing right now on the 99.99 objective, but we're losing the fact that there is a 1 week or 1 month period. So again, like we discussed before, there is no actual definition of what an incident is. If we have this 10-second downtime, it's possible that it's actually an incident. It's possible it's not. We don't know. This small violation, again, it's possible, but maybe not. If your SLOs are violated, so that means that at the end of the period, you actually consume more budget than you should. Yes, there is a problem. It's actually an incident on your side. But you would actually want to react before that. And if we look at period plus objective, then you get the notion of error budget. So to make it simple, those two graphs are exactly the same thing. It's just a different representation of the same data. So in the top, you have the SLI, the one we were seeing on the top, and the objective drawn as a big red line, but no notion of a period. On the bottom, you actually see what we call the budget. So in green is the amount of budget we get. So we get budget at every request. We'll see that later. And in yellow, it's what we consume. And what we see is that every time there is an incident or something weird in the SLI on top, then the budgets start to be consumed quickly. We start to use a lot of it. At the end, if we consume too much budget, then we will violate the SLO. So that means that we can start thinking of an incident as a percentage of budget that we consume in a short amount of time. And that's actually what we define as an incident. So if we consume too much budget in a defined amount of time, then there is something wrong, and then it's an incident. And it's actually important to have a definition of it. So everyone is free to define what is the percentage, what is the period. But in the end, if you make it clear to everyone, if you make it clear to your team, to your customers, to your managers, then when you do reporting, people can understand, we had an incident. That means that. But also when we had just a small hitch, maybe it's not an incident, and that explains everything. But when it comes to alerting, because this is the topic today, having a clear definition is very important, because you don't want people to get paged without a clear reason. So let's use this definition and try to alert on it. So we'll now alert on the error budget. So there's a big reference for that, which is the Blue Book, the SRE book of Google And they basically go through a lot of alerting techniques which are very interesting. And alerting an error budget is actually defined in that. So we'll quickly go through it because this is actually pretty solid. First thing is like the budget. So in the curve we saw before, the budget is just a percentage, like a price of your request. So if you have an SLO of like 99.99, then you just do 1 minus that, and you apply it to the number of requests. You get your budget. And the consume budget is the same thing without the 1 minus SLO thing. So it's not really readable like this. So let's just have a graph. So just for simplicity, I'll put an SLO of 80% because that's 1 out of 5. That's easy for me. The budget will just be 0.2, so 1 minus 0.8 times your request, and your consume budget will be the number of failed requests. And on the graph below, you can see what happens to both of the curves depending on the request. So here, for example, this is a successful request. So my budget increases, but the budget I consume stays to 0. Never positive requests, both increase. Never positive requests, both increase. And now I fail a request. When I fail it, I still increase my budget because the budget, the budget is for every request, but I start consuming some budget. So this yellow line increases, and so on and so forth for every request. At the end, so here we have 10 requests. We see that if we fail 20%, so exactly what the SLO allows us to, we have a consume budget which is equal to the available budget. So everything now will be actually based on this one. So if we look at the error budget in reality, so that's the same graph as what we saw before, you will basically see something like this. You will see some strong increase at some point, something happened, we don't know what. Then it goes tail again, something happened here, it goes. And if the yellow line, which is the consume budget, goes above what you actually have, then it starts to be interesting because you're starting evaluating your SLO. And when we speak about are you validating it or not, it's actually interesting to speak about how fast you're validating it. So if we go again on this slide, if we look at this part of the graph here, you press tail, so you don't spend much budget. So you're pretty fine. Here you start increasing. And this is what you maybe want to alert on. So you start consuming budget at a certain speed. And the thing is, you actually want to alert on this speed. If you consume budget very quickly, then something is wrong. If you consume budget not that quickly, but too much on a longer period, maybe that's interesting. So basically, the speed at which you consume budget is what is called the burn rate in that book. And this is what we also call it in that talk. So this burn rate is basically the amount of budget you consume to the available budget for a given period. And for a given period is always important. From that, this burn rate have interesting effects. So this value is 1. So this value of here consume budget of available is 1 means that you're consuming exactly your budget. So if you have a 30 days SLO period, at the end of the 30 days, you will have consumed all of your budget, which is not a bad thing. Let's remind that the budget is meant to be used at some point. So if you're below the 1, it's good. If you're just above 1, then you will actually breach your SLO. But then the bigger the rate, the faster you will consume your SLO budget. So if you get a burn rate of 2, it means you're consuming your budget twice as fast as you're supposed to. Then you will actually use all of your monthly budget in just 15 days. If you have a burn rate of 10, you will actually consume everything in 3 days. In real life, we've seen burn rates so high that you will consume all of your budget in a matter of hours. So that's where you can consider things. It goes to a very, very high number, but at some point, your SLO itself is a protection. So remember, like this 99.9% SLO is 33 minutes of downtime. This is your limit. You will never be consuming your budget faster than that. So we'll start alerting actually on this gradient because this is quite interesting. So we go back to the exact same picture again, and here is the burn rate on 1 hour of all these small spikes we saw. So this small thing here was a burn rate of 5, which was these spikes here. This big thing that we saw at the beginning, where we were like, should we alert or not? That's actually a burn rate of 10 on 1 hour. And this last one here that we were also seeing as like, it lasts for a while, it just go above and below. It's actually very low. It's a burn rate of 2. And then in the book, they give you some default values that you can try using. If we consider 1 hour at 14.4, then the interesting fact is that you will not have alerted on any of those. So you were maybe stating, should I alert or not? Actually, if you go by default, none of them consume enough budget for you to react. And they give those default values. They are pretty useful to start your system. And actually, in the long run, we kept using most of them except the first one because they were really showing all the time quite interesting outages. So that's the theory. This is quite interesting. Is there any question on the theory before we go to the more practical thing?
Let's see. No questions so far. I think.
No questions so far?
No, and I think we can continue, Yoann.
Let's go then. So let's move to the practice. So that's one is interesting. So at Booking we use MySQL as a database for many things, and MySQL is a master-slave system, as I guess most of you know. The problem is that sometimes the master has to change. And when it changes, it can go very quickly and go almost unnoticed, but sometimes it takes a few seconds to actually be fully propagated everywhere. And that creates these kind of huge spikes in our SLI. It just lasts for a few seconds, but it's actually very strong. If we look at the error budget that correspond to that, and we use the default value given in the book, this is interesting because this actually does not trigger the maximum criticality alert. This is not enough. So basically, problem comes, things got stale, and then we have a very small thing happening here. I guess you can barely see it. And this is enough actually to trigger the alert. And this is actually something that happened quite a lot at the beginning when we tried to use error budget alert. Basically, there is a change in the master on MySQL. Something goes wrong. It takes a few more seconds to propagate. And nothing happens. And then you get page, in this example, 45 minutes later. You get page, you get your laptop, and everything is finished. There is no incident going. There is nothing you can do. You just spent a couple of minutes checking all your updocs, going through your monitoring system and saying, oh, there was a master failure. Okay, and then go back to that. When it happens a lot, that's actually quite bad. But there is something that works well to fix that is actually using multiple windows. So basically, you want to do two things. So that's exactly the same graph, by the way. I just zoomed in. So basically what you want to do is alert if you consume budget. So you keep this same 1 hour window, for example, here, with the same burn rate, everything the same. You just add a second window, a small one, in the front of it. And for an alert trigger, you have to consume budget for both of these windows. So in that case, for example, with the MySQL masters, this was interesting because these 5 minutes here actually protect us from a small thing to trigger an alert later on. So either the drop is very, very strong and we get page, which is what we want, or the downtime is not strong enough, and then we don't want this small thing to alert us. So having those two windows works actually very well. And again, in the book, there are some default values. We actually use these two last lines, but not the first one. So why not using the first one? Well, there's something you need to know when you actually implement alerting is your monitoring system.
Hey, can you just go back to that previous slide for a second? I just wanted to say something. Yeah, what you're talking about here is actually, like, first of all, thank you so much. I'm so glad I'm hearing your presentation. I love it. But I just wanted to say something. What you're talking about here suffers a problem that moving averages are endemic to moving averages. And you can actually remodel this to use exponentially weighted moving averages and eliminate that effect and get the same underlying mathematical principles that you're talking about with comparing the burn rate at the different window frames. But the nice thing about the strategy I'm describing is that unlike moving windows, which require you to keep like a moving window worth of time and do some bookkeeping, exponentially weighted moving averages allow you to do it with like 1 unit of storage. So it's a nice alternative to this.
Okay, indeed. We can look into how this actually fits this model and see if we could actually use this instead of the small windows. I didn't try that.
Like one of the problems with moving averages in monitoring systems is that 50% of the time, the newest value in a moving average moves in the wrong direction as compared to the latest data set. And so right at the leading edge of a signal change, you can get the wrong result. And so by using something like an exponentially weighted moving average, the direction of change is always in the direction of the true change in the system at any given time. Anyway, it's something worth keeping in mind when you start talking about what you're talking about here is moving, moving averages, and moving averages have some unfortunate subtle properties that can be undesirable in a monitoring system.
Okay, thanks, Steve. I actually took note of that, and I tried looking at it. That could be interesting.
So, like, just to explain a little more, actually, a lot of automated stock trading systems basically do exactly what we're talking about here, and they'll trigger stock trades based on you can, using exponentially weighted moving averages, you can actually build like a hyperdimensional probability sphere and say how unlikely your value is given the different views of your average. So like it's the same thing as you're kind of doing here, but you can actually turn it into proper math. As soon as you do the moving averages, the math doesn't really work out because moving averages have some weird properties. Anyway, it's still a good system. I love this stuff. To be honest, I think it's really cool that you're presenting this. I apologize for interrupting. I'll shut up now.
No, please. It's actually very interesting. So thank you. This is not a talk. This is a community event when we basically want to speak with each other, learning from each other. So it's always good when someone actually shares knowledge. It's very good.
I would actually love for you to look at the projection alarms and see if we could do some stuff with error budgeting there. One of the problems with like doing alarms on bookings is that you lack any definition of good. You have to use some kind of model to like say what you should have had and then do everything based on that, and it adds a bunch more complexity. But yeah, I think this is really, really cool stuff.
And we can look at that. For the people that are not Booking.com people, to explain what Yves is saying, basically we have an alert on the number of bookings we get. So as you all know, like basically a booking company. And what we do is that we take what's happening in the past, in the history, and we try to predict how many bookings we're supposed to make at this exact moment of the day today. And if it goes down, we start actually triggering alerts. So this is what Yves is speaking about. Okay, let's continue. Thanks, Yves. So that works fine. The problem is that those windows sometimes can be tricky, and you have to know your monitoring system. So when we implemented that with this fix for the 5 minutes window, we started to get paged quite a lot, actually, more than we used to, which is kind of weird. And the reason is that actually our monitoring system did not allow for these 5 minutes to work properly. So we actually take lots of data on the client side and put it in some Kafka topic, get it, compute metrics, put it to Graphite. In Graphite, we take it into another system. All of the systems have caches, they have delays, they have things like this. And actually, we see that there is a few minutes at max between the moment the event happened and the moment the metrics appear. And if you look at it here, you actually see something very interesting, which is that at the end, I have no points. So right now on this graph, it's actually 441. And there is no data point here. So if we use the default values given in the book with 5 minutes to get the small window, actually we will have 1-2 minutes of data at best sometimes. And this will actually trigger lots of alerts because you want to have a window large enough to actually detect something. If your windows are too small, you will actually get into a lot of small spikes or things like this, which doesn't work. So if before you make any implementation of that, before you configure your windows, just make sure that you at least know the big lines of your monitoring system, know where the caches are, know where the polling is running, and things like this. Low traffic. Oh, this one is actually funny because this happened actually recently. So it's no secret to anyone that during the COVID situation that started in March, it was not easy to go to restaurants, to go to the museum, to go for things like this, mostly because they were closed. And the thing is that the number of people getting tickets for all of that started to decrease. So the traffic on this system started to decrease too. And we were starting to get a lot of pages. The relation at first was like, okay, what's happening? Did they change the pattern? Did the thing change? And the problem was actually different. I just see your thing, Javier, I will come to you after this one. And this actually only came from the amount of traffic sent. So if you want to get like a 99% SLO, you need to have some traffic coming depending on your window. So if you get this 5 minutes window, make sure that in this 5 minutes you get at least 3-4 times the minimum SLO thing. So for 99.99, it says you can fail 1 out of 1,000. Think of it this way, it's very important because if you say I can fail 1 out of 1,000 and you have only 10,000, then this one single request will actually trigger the alert, which is very bad. So make sure that when you have low traffic, you can actually extend the windows so that you detect real incident, anything happening for real, not just 1 or 2 requests. And if 1 or 2 requests is actually what you want to see, then you can also keep small windows or actually even use completely different things. But this is very important to consider. The Google book is designed by people that are handling system with high traffic. And sometimes it's actually harder to get the same thing working on some smaller system. So for example, here this museum system was not working well during the COVID. Javier, I'm going back to your question. What about self-closing alerts? Should those even exist? That's actually quite interesting. So we don't use it for all this error budget or SLO alert because we consider that if it triggers, we need to act upon it. As you saw in the severity things, if it's the biggest window, so like a window over 3 days that detects an incident, it just creates a ticket. So basically you have to like have a look at it, check what happens. And usually, actually, the funny thing is that the longer the window, the harder it is to fix it. Because it has something that happened for several hours or days to trigger the alert. It's usually not something easy to catch and trigger. I don't know if it answers your question, Javier.
Yeah, so actually, this is the situation that I have seen sometimes, that imagine that you have the success ratio that dips to 0 because you have an outage. Then you wait for some minutes, and then automatically, because it fixes because it was something else, it climbs to 100%. So in that window, nobody acted on the alert, but I have seen some systems that they automatically close the incident open. So the question will be whether that makes sense or not to have these alerts that close automatically, or if we hit the pager, it means that somebody has to close that.
Yeah, so that is actually interesting. Like, from our point of view, and this is only personal, so maybe other people have a different view on that, and it would be interesting. We think that if there's an alert, there is something to check. That's the first thing. Like, if it's so critical that you spend 2, 5, 10% of your monthly budget in a couple of minutes, then someone need to have a look at it, because the damage can be inexisting. Like, if it's a MySQL failover, for example, you check, there is a failover and it's gone. So you go back to your life. But sometimes it's actually just something that prevents you, not prevents you, but it's a symptom of something bigger that may happen later. So usually we prefer to actually watch what's happening. So for this high severity thing. For the lower severity, we actually just let them open for them to not trigger all the time. Because this is something that happens a lot, especially with this window thing. So you have like a 6-hour window. Let's say you close it automatically, then it will go close, and the 6 hours is huge. So it will actually trigger by itself again as the smallest thing coming on top. So it's actually quite hard to have auto closing window for the smallest criticality here.
Yeah,
I don't know, but other people may have different views.
No, I mean,
Guys,
I think that if, from my opinion, I coincide that if you have something that hits the pager, you should have somebody human closing it, because if it hits the pager, it's something that is very important and requires human intervention.
Okay. Is anyone thinking the opposite? That would be actually interesting. Is anyone using auto-closing alerts for any known reason?
I would argue that you know, if you're opening and then like really quickly auto closing an alert, your alert system just isn't tuned right. I mean, we have definitely seen this problem in some of our alerting stack at Booking for sure. You know, as you said, there are generally strategies that you can use to tune your alerting so that it tends to see through routine like glitches. So a lot of algorithms will, for instance, give you, as you said, a window size that exactly what you're saying. It should consider the traffic. If you're not getting enough data in 30 seconds, then to make a good decision, you need to consider whether or not your window should be a couple of minutes. A lot of times when people get monitoring wrong, they're basically just looking at too little data to form like a general trend line. You know, if you think of the average of like the number of errors you had in the last 60 seconds, if you get a really big burst, then there's some arbitrary size of that burst that is going to trigger your alarm, even if you only had 1 second of it. So, you know, there's a bunch of ways to kind of deal with that. Exponentially weighted moving averages is one, like basically smooth the curve. But like attenuating your window size seems to me to be pretty important.
Okay. And I think we are on the same line for that. If anyone just wants to share anything, please use the chat and speak about it. It would be quite interesting. Okay, so we now have adjusted for low traffic. And then there's something again funny for that, is having customers with actually different loads. So when you look at your SLIs, usually you try to aggregate all of your customer or a huge chunk of your customer into one metric. And then you will actually base your alerting and your reporting on that metric. What we've seen is that this is sometimes hiding a lot of problems. So we have, for example, for one of our systems, 2 customers being 80% of the traffic. So if one of these 2 customers have a small issue using our system, we will know quickly. It will quickly trigger an alert and everything. And then we have some customers with 1% of our traffic, less than that. For them to actually create an alert, it's very hard. They have to be almost unable to use the system at all, or sometimes we won't even see it point. And this is a problem. We had a case a few months ago when we had a firewall issue, and one of our customer, which was a very important customer, couldn't use our system. And we had a small C. We could see the SLI being a bit lower than usually, but it never triggered any alert, and we just found it by luck. So this is actually a good example of like, try to get to know your customers, and if some of them are actually very, very important, try to get an alert for them if they send enough traffic. And that actually will make things very good, not only for you, but also for your company in general. Also, if you have lots of people with small traffic, maybe you can aggregate them. So, for example, in that situation I was speaking to you about, so we basically kept this big SLI alert, and then we started to have one alert specifically for these very important customers. And then we had one or so with all the ones that are sending very low traffic, but all accumulated. So it's around 10-15% of our traffic. That is one single SLI. And so if one of them start having problem, we start seeing things in that case. So think about it. When you have customers with very different loads, try to actually have multiple alerts for your exact same SLI just to see everything, or at least see more things. Customers with different behaviors. Oh, that is actually something that we see way too often. So let's say you have a small data retrieval system, and you can make a request to this system. And when you make this request, you can ask the data for any given number of items up to a certain limit. So I will call my system, I will send it a request and say, okay, I want 10 items. Give me the data you have for these 10 items. And it's fine. Like my SLI latency will be fine. My latency SLI will be fine, sorry. And some people will actually fetch 100 items at once. Okay, it's still fine. And some are actually fetching 10,000. So actually, I don't know where is the limit, like where it starts to take too long. But in the example we had, so that happened a month ago, people were fetching up to 10,000 items at once, and the SLI actually wasn't working for that because we allowed just a certain number of milliseconds, and fetching 10,000 items actually was taking more than that. And just to make it even worse, it was a cron job, so something that actually ran at a given period, and that was actually sending only this kind of request every few hours. And it actually triggered the alert every time. So when you have different behaviors, make sure that either your SLIs accounts for any given behavior. We basically add things with like search engine or something like this, when you can actually start to build your SLI with expectations that are different depending on the request. Or sometimes you can also put a limit. So in this simple example, we say to the customers, okay, guys, you can fetch 100 items. It's fine. It will fully be counted in the SLIs. But if you fetch more than a certain limit, in that case, it was like 500 or something, then you're out of the SLIs. We don't want to consider this kind of request as good. If you do that, you start missing out those people, so you can keep a metric out of it. And you also see the state of your system. So if too many people start sending these big queries, they might impact the people sending small ones. So you can still see the behavior of your system in a good way and say things. Another alternative that a lot of people use actually, and we use it once, but it don't work much, is to use a probe. So you actually create a system that will send well-known type of traffic and then try to monitor how your system reacts to this exact traffic. So you have many solutions, but make sure that your SLI basically take into consideration that your customers may have very different behaviors. And the last point is just an example we have to show that this error budget thing is good. It works pretty well from our perspective. So we use it for 2 years now, and we cannot complain much. It's working very well. But sometimes you need to go back to the old system, to the technical metric system. Here's a simple example. So we have a service that is processing items. In our case, it's processing reservations. It's sending things to a queue. So in example, it's a Kafka queue. It's being consumed by the service, sending again to another queue, it's consumed by the customers. And we want to know if the job is done well. So we have a completeness metric that we take. So we have built an app that actually takes everything from here and compares the output from here and makes sure that everything is at least present, that everything is a good shape, that all the fields are set. We cannot know what is the value, but we know if it's set. We know all those things like this. And for this app, when we want to use the two windows, checking that everything sending from service 1 is available, is available in this queue in less than 2 minutes, that works pretty well. We can use this burn rate alert and everything. But when we want to start increasing this window and saying like, okay, we want at 24 hours to be sure that everything is there, this starts to be hard. Basically, you start to, again, have things that are not actionable or things like this. And it just doesn't work much. What we actually did at the end was just like, this one service was just pushing everything to Hadoop all the time. And we were actually, we don't see it here, but from this monitoring app, we were also pushing everything to Hadoop. And have just a job, comparing everything, making sure that everything is fine, and then sending us a technical alert this time, saying like, okay, guys, too many reservations are bad. Please take an action upon it. So we know something is really happening, so you can really act, but we don't send page first because it's not really actionable directly. And we have something that says page anyway. And there is no way of having windows to catch all these things because you can have very small numbers that have triggering issues, and some of them can be very far in the past, so it just doesn't work. Another example we had with this exact same system not so far ago is one of the Kafka broker having issues. So just disk issue, for example. If you look at it, on a global system, you might see your SLI still being fine, which is good. But at some point, this broker starts not working properly. And the latency of people fetching from it, which is completely out of our system here, will start getting increase and increase and increase. And we didn't find a good way to catch all of that issues, apart from starting to have a good OR metrics that monitor the CPU or the disk on this Kafka broker. So it's very specific, but at some point, if the disk is full, you need to know it. And especially in a system that has, and this is the case for this thing, a very small number of instances. So when you get a system that has 1,000 servers, the SLOs are fine, no problem. When you have 100 boxes, it's still usually working fine. When you have 2 or 3, then a single box having issues can impact everyone. And this is exactly the case of this Kafka broker. So sometimes you need something on top of the alerting, of the error budget alert. So yeah, that's all for the examples I gave. If you have more questions or anything like this, we can always discuss that. I'd be happy for it. But yeah, in a given amount of time, I have to make it short. So we've seen, okay, how the alert actually works, how you can tune it, how you can prevent some false alert to trigger or catch things that you will not see. But at some point, you want something generic that just works. You don't want to be always tweaking your system. And usually, actually, the default values that are given in the book or in most of your automated systems are quite good. You can already use that. And if you are today using technical metrics to alert, you will see that using the default on error budget alert is very efficient. Another thing we see is that the SLIs in general, actually, they are generic. If you have a simple HTTP server, you will see that you have an availability SLI, you have a latency SLI, you have some other stuff, but it's usually quite generic. So you can at least build a system for this very common SLI and make it available. And it's actually what Gareth's team did. I see not most, but many of them are in this presentation today. Basically, they actually built something that does the generation automatically, so that if you build a service today at Booking, you don't need to do much to get all of what I spoke about with Eve and Javier for half an hour, just in a click. So basically what they did is pretty interesting. So the first part is how monitoring works with booking on client side, I mean. So I have traffic that you send from one client to your service. And on the background, this client is sending some what we call events that contains metrics for how you use the service, how you view the service, and things like this. You put those into a Kafka topic. And normally you just generate metrics and put it into Graphite. But what they did is build on top another service here, this SLI generation service. That actually take all those events and based on some configuration, start to store SLIs directly into Graphite. And as we said, like many of generics, so for the generic one, it works fine. You want an availability SLI, just works. You want latency SLI, well, just define what is your threshold and it works. So it's pretty good. So it goes to Graphite, and then we use Boson to send alerts. I don't know if many of you are familiar with it. You can just check out. But basically what this does is take data from any time series storage or thing like this. You can even take it from more things and then start aggregating them and then doing alerts. So this is actually what it does. So this Boson system will retrieve all the metrics that are sent by this system. How does it know that it's those metrics? Well, it's just a single path. All of the metrics have the same prefix. It goes fix, it takes all the metrics, and then start to send notification of all the things happening to another system, which is have alert API. And then the product owner, I just have to click on subscribe and get the alert sent to him on PagerDuty. So that's actually very good. I've seen that there's lots of customers already for it, and this is pretty awesome. Like all the things you have to do to go to this system is just one click and one configuration file here. So it's pretty good. So this is good when you're on premise, when you have time to build something. This is very efficient. But maybe some of you are actually in the cloud. So in the cloud, you actually can do the same thing. I've just checked it out. And if you go on GCP, for example, you can actually create some SLI alerts that are exactly doing error budget alert in the background. You can configure your window. You can configure your burn rate. So remember this 14, 6, and 1 that we had at the beginning. And then this gives you a report, and this sends alert only if you consume this amount of budget, something like this. The problem with this is that you don't have this multi-windows thing. So maybe actually the thing of using the exponential moving average AV is very interesting in that case. But maybe they will also put this multi-windows thing at some point. So just for you to know, like it's very, very easy to use. Just create your SLI here, configure it, put the alert, and it's finished. You will receive the alert only if you actually spend some budget.
We have some, going back to the schematic where you show the connection with events. Can I just make one little minor point?
Sure.
So one of the things here is that omitted from this diagram is that we actually have a number of other systems that send alerts, which is why we have Alert API. Boson is just one of them. Boson sits behind Graphite, so there's a certain amount of latency between data going from, let's say, your service through the events pipeline, through the SLI generation pipeline, into Graphite, then queried by Boson, and finally sent to Alert API. For really critical, like business sensitive metrics, like bookings, for us, we would have something that is sitting basically where it says events on the diagram, and it's actually doing some very similar stuff to this that has a web page that you can set up. That will send an alert directly to Alert API right way before any data even gets to Graphite. So we would only put metrics into Boson, alerts into Boson that are tolerant of a little bit of extra latency in the pipe, whereas things that are very low latency tolerance would come much early in the pipeline. But essentially, we would do the same things.
Awesome. So actually, when we said we need to know the monitoring system when we put alerts, that's a very good example. Okay, so this is that, and basically, yeah, it's the last slide. So then it will be your turn to speak, but just summarizing what we went through. So just try to make clear of what an incident actually is. That might seem like not much interesting, but actually it has a lot of usage even outside of pure alerting. When you want to report, when you want to make sure that your customers are in line with you or something like this. So try to define what is exactly your incident definition. For us, in that case, that was some budget used in a certain amount of time, but it could be different for you. So just make sure that this is clear to you and to people using your system. When you do alerting on error budget, so you can implement it. There are many ways to do it, and it's very powerful. To be honest, we were receiving alerts every day 2 years ago with the technical metrics, sometimes more than once every day. Moving to this kind of system was actually very good. It reduces strongly the number of alerts, and it also makes people happy. It's hard to say that people are happy when they get paged, but at least when they get paged, something is really happening, which is quite good. And the last thing is that configuring all of that can be sometimes tricky, and if you can make it generic, as Gary's team actually did, or as you can use in the public cloud, then just do it and start with that. If you see that some issues are still there, okay, so try to get through some more, but at least start with the default. It's really well. And that's it. If you have any question, go for it. And if you have any experience that are different with using error budget alerts or using any other kind of alerts, please share it with us. It would be very interesting. Thanks.
Thank you, Yoann. So yeah, following on what Yoann said at the end of the presentation, if you guys in the audience have different experiences and you use alerts in a different manner, please feel free to contact me, and maybe on the next event you will present how you deal with that. And the purpose of it is to share as much as possible experiences and learn from one another. So I'm looking forward for you to actually propose new topics for next editions. Any other questions related to alerts? No, it looks like we don't have any more questions. That being said, I will conclude the event for today, and soon after we stop the recording, I will follow up with the recording upload on YouTube and hope to get some feedbacks from you guys. Thank you so much for attending this event. See you next time.
Bye, everyone.
Bye-bye.